All right. Hello. I'm from New Jersey. I took the train here, Amtrak, and on the way here experienced a really interesting phenomena. I guess it was the not quiet car. 4 people around me were basically selling unicorn coloring books, or LLMs. Someone must have worked for Google, someone for AWS, maybe someone for Red Hat, not sure. And I kind of had an existential crisis moment sitting there, working on a talk, wondering, what am I doing here? Like, I've been doing this in this field for 10 years. Everyone is working in LLMs. Why am I going to Boston? What's the point? And I answered it to myself, but I can't say much more until I read you this legal disclosure. Nothing that I say should be used to make any trading decisions. This is not trading advice. And a bunch of other legal things. But yeah, don't take anything that I say seriously with respect to what you do in open markets. So why did I come to Boston? I could have stayed at work, and just done that thing. But I realized over 10 years of my career at 2 Sigma, I've been really successful building compute systems by leveraging my network, both in academia and industry, and using that to inform what to build next. And I'm going to show you 4 different times where I've been able to do that. But it's 2024, and the truth is, I don't know what to do next at all. And I'm reaching out to this community and other communities to strengthen and build my network so I can learn from you all, and we can share ideas so that we can figure out collectively what to build next, because I'm pretty sure the scope has gotten so much bigger in the last year that it's not something that I can come close to figuring out. I guess that leads into about me, but first I'll do about 2 Sigma because I guess I'm commingled with my work at this point. I think this is a screenshot from 2015 or 2016, and I thought it was pretty amazing. We've been doing machine learning at 2 Sigma since I've been there in 2011 in very advanced ways. And so much that this is at the top front page of our website. So we are a financial services company. You could call us a hedge fund. We do trading. It's all systematic. It's not what you may think of a trader making a decision surrounded by lots of monitors. I don't know that I've seen a trader in my tenure there in person, but I've seen thousands and thousands of computers, or at least have seen that they exist. But yeah, we really are using science, machine learning, and distributing compute to guide decisions that we make in financial markets. And that is so true to the core. And my role within that is, you can maybe look at this asynchronously, or if you want to look me up. I'm the head of IM platform engineering. And I've sort of had almost the same role for 10 years, just with increasing and increasing and increasing scope. I joined 2 Sigma in 2011, and within 2 weeks, my boss had said, okay, you own the sim farm at the time, which was 100 computers in Pittsburgh, New Jersey, that I was then responsible for. And I've worked to extend that sim farm from 100 computers, which was about, I don't know, not even 100 terabytes of memory, no, to what it is now, which is a petabyte scale compute cluster that we run to do all our model training. Thinking about this talk and my history, I wanted you to take 3 takeaways. One is that our platform, as I've seen it evolve over the last 10 years, is always a reflection of, or the rear view mirror view of what's happening now. So the platform we have today isn't really suited to the problems we have today. It's well suited to the problems we had 18 months ago or 2 years ago. And it's constantly evolving at the edges of it. As I'll get to later, it might be a little more uncertain now, but over the last 4 cycles, that's been fairly true. Something pretty obvious, but that I've seen, is that just throwing scale at the problem does work. So in 2013, we were using multilinear regression to solve forecasting problems. Today we're using large neural nets, maybe some large language models. But the technique is less important than the scale itself. And as long as we continue to chase scale, I think we'll continue to be successful. It's just that the scale is so big now that we can't do it alone, which is the third point. The only way I think we can do this and to keep going as Two Sigma for the next 10 years is to double down on our collaborations, to double down on working with industry and academia to see around the corners and to see what's coming next, and continue to scale that way organizationally, as well as buying thousands and thousands of computers, which we also do. So yeah, what I wanted to do for the rest of the talk is try to give a sense for what I care about, what Two Sigma cares about, what problems we're trying to solve, and then how we've used compute over the last 10 years to solve them. I've used these slides before. Sometimes they land, sometimes they don't. I'll give it a shot here. But really, everyone at Two Sigma is collectively solving what we call the learning problem. It's a learning problem just like in the last talk. They have the same learning problem. We all have the same problem. In grade school, you probably learned this as y equals mx plus b. Like there's a simple relationship between x. In our case, x may be the price of oil, y may be the returns on Exxon stock or something like that. And again, that's not advice, that's just a relationship that probably exists. In linear algebra, you learn that x is actually a matrix, and x gets very, very large, and y gets very, very large. Theta is your parameters, or your model parameters. And the whole point of this, of really being at Two Sigma, is to minimize that small epsilon. So x is all the data in the world, and y is anything that we can predict or trade on. And if we can get that epsilon to be 0, we can effectively predict the future and, I guess, print money, you would say. So how do we do that? We need a lot of computers. So we can specify this objective function. We can have 100 modelers work collectively to solve this, but then we need to do model training. And the learning problem looks like that in most places, but Two Sigma is unique in that we also have to run simulations on top of our trained models to see what would happen in the real-ish world, or at least our collected view of history on these models. So I think that's new and unique to financial services. I see a lot of people stopping at training and then deploying in the real world or testing out sample. But here we can see the real world effects of what we're doing. So we have a complex and layered problem that we're trying to solve. And now we'll talk about the 4 ways that I approach solving this, 4 generations of compute, and I guess 10 years of solving the learning problem. There's always a pattern here. We have some business problems. Something in this learning problem isn't working. We need to improve it. We have one kind of big idea. Because we're not a huge company, we can't have 10 big ideas. We have one central idea that we're going to apply. And then we build out an architecture, and we use it to address that business problem, and we kind of rinse and repeat. And we've done this 4 times so far. So the first problem, and this is when I first landed at Two Sigma, was the simulation problem, which is that these sims were 80 gig JVM processes that needed to be distributed and run across 100 computers, and many modelers needed to run these at the same time. They were competing for resources using our primitive at the time job scheduler, where each modeler got 2.5 terabytes of memory that they could use. So they could only run a handful of jobs. But if we only had, let's say, one modeler in the system at any given time, like Saturday night at 2 a.m., the rest would be wasted. This didn't seem like the right way to approach using our computers, so I pulled on my peers. At the time, I was close with Berkeley Amp Lab and what became the RISE Lab. So Ben Hinman had written a paper on Apache Mesos. We were in touch, and we said, what if we built a Mesos framework that would allow us to fairly share resources across all of our computers and even extend that into the cloud to overfill jobs. So this isn't a very deep and technical talk, but I'd rather leave you with some breadcrumbs. Please check out the Mesos paper if you're interested in systems. It's one of the best, I think, over the last 10 years. We've successfully used that to build out this system. It was a fair share scheduler that minimized waste from some sometimes 60% waste, down to even we were using our computers like to 90% efficiency. And that was great for a little bit of time until the next problem happened. The next problem was the X's, I call it, or just big features. This was the explosion of big data, 2015, 2016. You couldn't get enough data, right? There was alternative data sets were coming in. There was such demand, and the data sets had gone from being maybe 30 gigs to 300 gigs, 300 terabytes, and huge. And the only tools we had in our toolbox to analyze big data sets like this were like naive MapReduce that we had built ourselves. The innovation or the big idea here was pulled from Matei's paper, the RDD paper, Resilient Distributed Data Sets. I think he turned this paper into like a $2 billion company, which is good for him. For us, it was useful in that we were able to process a lot of data using basically a Spark-based system. Really naively, the idea is that you take your data set, which can be very, very large, you partition it into small pieces, and then you can run compute over pieces of that data. We got a lot of mileage out of this and actually built out our data processing kind of capabilities to the point where that was no longer a bottleneck. But then, of course, the next bottleneck arises. So this is always with systems. The next bottleneck continues to happen. So the next bottleneck was we had a ton of data. We had built a lot of models, but we couldn't actually deploy them because I think an earlier speaker also spoke to the same thing, is that modelers were writing these models in any framework that they can get a hold of. And in order to take them and productionalize them, we would have to go through a lengthy process of rewriting their code to be able to write this in a format that we can then deploy and scale out to production. So there was a great paper out of Microsoft, the Onyx paper. It proposes a standardized runtime for running machine learning models. We were able to standardize on Onyx, which is that middle blob, as a runtime that gives us a layer of indirection between the modeler's code and the deployment targets. And then so Onyx models can be deployed to run and do inference in real time. And this accelerated the pace that we could productionalize models. And then production's not a bottleneck. But now the big bottleneck, model training. And I think that's where we're going to be stuck with for some time. What we're seeing now is models that are sometimes millions, even billions of parameters, because it's easier to create these models, and now 100 terabytes of even features. We're new at how we're approaching this, but the problem we had with shared clusters and shared compute clusters for doing this is that reliability of the clusters is just not there to have like repeatable, reproducible workloads. So we came up with the idea that we lifted somewhat off of the Ray paper, which is also out of Berkeley, is the notion of disposable clusters, that you can stand up your cluster at the beginning of a model training session, run it, it should be repeatable to run, and then tear it down at the end, where a model training session could be 2 weeks or 3 weeks of training. The Ray paper itself is sort of the platonic ideal of a systems paper, I think. It's a great reference on how to just build a distributed system and think about it from first principles. And we take a lot of ideas from it. I don't mean to say that like 2 Sigma is a Ray shop or anything like that, but we have lifted a lot of these ideas, especially the global control store and the object store for scaling machine learning. So this is kind of the recap. What I've experienced is this set of S-curves, right? So we have some new innovation, we accelerate really quickly, and then that problem becomes a problem in the past, but then the next problem comes up, and we're kind of flattened out for a while, and then we accelerate again. And we're somewhere around 4 here, and we know we're in a period of great acceleration, but definitely I feel different this time in that there's so much more uncertainty. I don't think there's one big idea that we can take away. There's not one key paper that one could pull from to get us through the next 2.5 years. It's a point where things are just exploding. And I really felt that in my experience on the train when everyone was talking about LLMs, and I was just sort of baffled. This is just a few of the things that we were thinking about and a few of the problems we have. So it's really sprawling out. We know these things are coming. We know that we're working on them, but we don't have nearly the size of people or enough people to put, each of these is an entire research agenda. How do we efficiently use GPUs and not waste them in I/O cycles? We want to build high performance algorithms for time series ML. There's so many things. I'll walk through some of the challenges that I have because I think I have some time. But again, I think it comes back to this point. Like, this is now too many things. It's too big for us to go it alone, and we want to collaborate. So that's where I think we get to the MOC plus 2 sigma, I guess, value proposition here. I can come with lots of problems. Some people say, like, there's a paper idea a day at working at 2 sigma, and I can kind of broker those out. We can share, we can find students, we can find opportunities. It's just a matter of how much we collaborate. The fun ones that I like to look at are GPU efficiency. How can we quickly get data to the GPU and use them efficiently and not waste them? We have amazing data. I call this class of data exhaust data. It's like, we can't share our 2 sigma data. That's private, like financial data. We can't share our models. But the stuff that comes out of the exhaust of our systems, trace logs, GPU utilization metrics, things like that, I think are a great asset and a great wealth that we're underserving now and could share more of as we collaborate. High performance algorithms, it's pretty wild, but we still see common techniques that machine learning researchers are doing every day are like n-squared complexity, and just, it's right in front of you. And you can see opportunities to get down to like n log n or less. And it just takes time and work and analysis to do that, but the impact and the leverage is phenomenal if you can do it. We have a whole team dedicated just to doing this. This is meant to be there's such a sprawl of foundational models. If you looked at, like, I don't know, there are 20 released every week, maybe there are 5 released every day. Like, how can we even keep track of these and compare them and evaluate them? It's a big area for research for us going forward. Fine-tuning models is another place where we're just getting started. It's pretty difficult to do this within 2 Sigma's firewall. And so having open source partners where we can do experimentation on synthetic data sets that aren't real but give us experience doing fine-tuning. We bring some expertise to the table to how to set these up, and we're looking for partners to work together to do things like this. And finally, just this baffling statistic, or baffling number. Someone asked Sam Altman how much it cost to train like GPT 3.5 or 4. And he said, was it 100 million? He said, no, probably more. And at that point, like, you talked about money and like access to equity and who will control it, but not everyone can play that game, not even 2 Sigma. We're not going to train models that cost $500 million to train. There's diminishing returns. So looking for like low cost, low rank approximations, like lower precision ways of training, but we still know we want to train our own models, is another big research area. So I took a shot at kind of a matrix. I think Larry helped me work on this, but these are just my ideas of how we could work together. I mentioned it before. What I think you all have is on the right-hand side, and what I know we can offer is on the left. Like I said, we have pretty well-specified, reproducible problems with benchmarks that it's possible for us to share, and we'd look forward to doing that. And they're very unique, I think. Especially in the area of ML AI, where we don't really need proprietary data anymore. We're doing a lot with synthetic data sets. That's recent as of 2023, so we can begin to share more. The exhaust data that I mentioned, I think would be a great opportunity. And then finally, we do use cloud resources. We use Google or AWS maybe. And that limits us into the way that we can experiment with hardware. And so having a place where we can get more and look at the full stack of hardware and build training clusters that take into consideration storage, network, the full stack of the training solution would be a great opportunity for us in MOC, where I think we have not built out that experimental capability on our own. So that's the call to action. That's my ask. I'm here all week, so we can talk about that, and please reach out to me. Thanks. Yep, I shut it off. Oh yeah.
Hi, super fascinating. It was really fun to hear that longitudinal look backwards over those 4 generations. And so this relates to actually, the question relates to that and 2 of the lines in your collaboration chart. So what I was struck by, and I'm always struck by, and Rudolph brought this up in the last thing, training, learning, the learning problem, looks a lot like scientific computation. Over the years, the US government has subsidized the construction of systems like Blue Gene and other systems, which have a much better density and interconnect fabric. But I saw a very consistent commitment to the hardware platform through those 4 generations. Do you think you've reached the inflection point where, okay, maybe now we have to consider something that is not considered just commodity, but can actually be towards, because I mean, we're moving in these very strange ways, right? A GPU is not commodity, except that now it's commodity because we made it commodity. A TPU is not commodity, but it's going to become commodity. And yet we're always stranded behind just, for bleep, interconnects, right? The interconnects are horrible. The connection to the density and latency to the RAM is horrible. And so I'm curious, do you think that that's one of the things forward? And then I'm really curious about the exhaust data. Like, what do we practically do to get access to the exhaust
do that?
data?
Yeah. Well, luckily, I have peers here who are pretty closely connected. John Stumpf is here. Larry Rudolph, who I've worked with for, since he arrived at 2 Sigma, has been a mentor to me. And they can both help, I think, on the exhaust side. I know Larry and I talk about it a lot. We want to make it happen. So we'll have to figure that out. On the, the question, I guess the first part is like commodity. I feel like we've exhausted our ability to innovate on commodity hardware. I think that we probably spent that is like everyone in distributed systems has spent like the last 4 years building out abstractions that work together to like do integrated workflows, things like Kubernetes pods or like the best practices for building out these training things at the expense of optimization. And now optimization is the only thing we have left. So we can't really, if you saw like Altman's quote, we can't just scale out to like $100 million worth of computers and like get sloppy about it. Like if you can not be sloppy about that and you can do that full stack, we see like 10x, 100x improvement opportunities maybe, possibly. But we need a proving ground and partners, and we need people who can work on that with us, whether they're in industry or in here in academia. But yeah, my hypothesis is we're kind of done, at least in 2024, on commodity hardware, unless you're doing naive things with like services or something. But even once you get into fine-tuning and other things, it becomes optimization. And so that means like retooling, rethinking much of what we built over the last 4 years, and then even skill sets, how we engage, and what we do going forward. So it's definitely a critical shift and a critical time, I think, in the history of distributed systems. Like if you look back the last 10 years, it really was kind of simple to know what to do. Like it wasn't rocket science to use an RDD. It was like, do it. Yeah, like find Mesos, Kubernetes, they're basically the same thing. Now, no, I think you really need like a much more deeper approach and to be much more scientific and rigorous about it.
So this is great. I sort of see a lot of, like, it's been really fascinating for the last number of years interacting with you guys. And you've built a lot of also either bespoke or proprietary internal systems, not that you necessarily want it to be proprietary, but because in some sense your problems, or at least you thought your problems were unique. And then I look at, and a lot of those problems I think were just maybe a little bit in advance of other people realizing they had that same problem. So is there, like, I'd love to see exactly what you're talking about, that engagement of building new things with new characteristics in kind of an open place where we can innovate or bring in the AMDs and Intels and others with GPUs or TPUs and stuff and be experimenting with that. Is that something where, you know, we could imagine sort of you have the requirements, but then we build a new system together? Is that sort of external, developing it outside of Two Sigma?
That's what I really aim to do. It's you know, my next 5 years goal is to get to the point where Two Sigma is doing that. So when I opened the talk, I said that, you know, our architecture reflects the rearview mirror of the last 2 years. But like, what's looking ahead the next 2 years? We're a bit, you know, limited and reactive. I think through partnerships with the Alliance and others, we actually can do that. And we can do that, probably to your earlier point, is because like workflows are becoming commodity. It's about like data. If you can get synthetic data, which we know the distribution of our data, so we can build synthetic data sets, we can share a lot more than we could even back in like 2018, where we really didn't have our head around like what machine learning was going to be at that point. Now we have like very contained, isolated workflows. These are model training jobs that run on some, you know, maybe 400 to 4,000 GPUs at some points, but can also be like estimated at smaller numbers and taken down, where like students or people, you know, here can actually like get their head around them and work together to building out a reference architecture for like the next, you know, number of years. So yeah, that's really answers that existential question: is why am I going to Boston? Same reason I'll go to Berkeley, you know, in 2 months. It's part of like getting people together to work on this problem collectively.
And so if you just flip it for a moment, I mean, you're saying that in the past this was a proprietary advantage, but now it's not, so you could feel more comfortable building these new systems in the open? Is that?
Yeah.
Is there any difference? Maybe just.
I mean, there's going to be a line, right? And you know, we've built a lot of systems where we encapsulate the pieces of intellectual property that we still wouldn't share. But like, I guess we're computer scientists. We can build black boxes around those things. So whether we're using, you know, linear regression or something different, kind of the learning problem is the same. It just has a different profile. And we've learned, especially because we have interns, we have people who just work for their first year at Two Sigma. We don't give them access to like all the data and say, you know, go to everything. So we've learned as we try to onboard new people that we need to simplify kind of the problem and control access to what is IP and understand that better. So training, you know, a giant model at scale, even maybe there's some techniques we couldn't share the name of, but we can give approximations to those that have like open source equivalents or in the same family or model hierarchy.
So one last question is that, do you view, just looking forward, there being unique problems for you that aren't general? Like I remember talking to Mark way back when, and he was talking about how you wanted to retain the provenance and certain things like that. And I was thinking, oh my God, that would be so useful for academia if we could do those things. But I'm just curious, do you sort of perceive that there's unique problems you have that are either not interesting or that one wouldn't want in a general platform? Or is it, do you really feel like it's much?
No, there are definitely big classes of unique problems that we have. Training or techniques for doing like large LLM style machine learning over time series data and treating like time series as language is a research area that we would not probably be comfortable sharing. It's very like unique to what we do. Even the notion of time, when we start talking about like time in general, there are actually like proprietary ways that we think about time and bitemporality. There are things that we wouldn't share, but they're always encapsulated. That's what I found. And the organization is such that that encapsulation or that containerization is both how we build software and also how we're structured organizationally. And so I realized that that design actually does give us opportunity to now reach out and share more. And I just don't think that was apparent, or we had the right people in place to form those relationships in like 2018, 19. I remember I actually was here in 2019, I gave a talk, and then like pandemic hit and it all kind of got reset. So this is sort of me like saying, I'm over that, like we can start again. Yeah. But I think we're well better suited to do it this time. Cool? All right, thanks.